Hi and welcome to Physics Hi, and today I'm going to go through the answers of the short answer section of the 2022 HSC Physics paper. But before we start, please remember to subscribe and hit that bell to get my latest updates, and please consider supporting my work by buying me a coffee. The link is in the description below. So let's get started. Let's move on to question number 26. And in this case, 26 deals with the photoelectric effect, which is part of the module 7, where we're dealing with the quantum nature or particle-like nature of light. And in this case, it's a little bit different to what you may have learned in the school. What we have is the photoelectric effect. Light is striking a surface, and that is releasing photoelectrons. And now it moves through an area that contains also an electric field. And the question says there's a certain frequency to the incident light onto our calcium metal, and we're told it has a work function of 2.9 electron volts. We know that they're overcoming that work function because photoelectrons are being emitted. We also have the application of our electric field of 5.2 newtons per coulomb, which is perpendicular to the plate. Now it says, first of all, show that the maximum kinetic energy of the emitted photoelectrons is that particular value. Well, this again is one of those questions where if you end up struggling with the first part of the question, you may actually have a way of working at the second part of the question because it already gives you the answer that you need for the second part of the question. This is all about that the kinetic energy of the photoelectrons is equal to HF, which is the energy of our photons minus the work function. Now, got to be careful here with the units. We've got frequency in hertz over here, and we have the answer here in joules, and yet we're given the work function in terms of electron volts. In order to work out this, we say, okay, that's fine for Planck's constant. It's 6.626 by 10 to the negative 34. We multiply this by the frequency. Again, this is given of 7.5 by 10 to the power of 14. But now the work function has to be included, and we're told it's 2.9 electron volts, but we have to multiply this by 1.6 by 10 to the power of negative 19 to turn that into the unit of joules. When you do that calculation, you're going to get 3.2 by 10 to the power of negative 20 joules. And that, of course, is the answer we are looking for. Now let's look at our second part of the question. It says now calculate the maximum distance that this photoelectron actually moves up. Well, how do we determine that? Now, in order to stop our photoelectrons, work has to be done on our photoelectron, and therefore we have a change in energy. And so what we have is our work done is equal to our voltage multiplied by our charge, and our voltage is the electric field strength multiplied by the distance multiplied by the charge. Now the work done, well, that's the work done that basically makes this stop. So in other words, this is 3.2 by 10 to the power of negative 20. Now this equals our electric field strength, which is 5.2, multiplied by the distance it moves, which is d, and multiplied by the charge. And now it's a photoelectron, so therefore that's going to be 1.6 by 10 to the power of negative 19 coulomb. And so now all you need to do is rearrange this, and you get d is equal to 0.038 meters, or you could say that's equal to 3.8 centimeters. On to question number 27. Now this particular question deals with module 7 and the wave nature of light, though we'll see in the initial part of the question it actually challenges that view. And so what we have here is what we would see as a double slit setup. And so we have a light source right here, our slit over here, and our screen further down. Now the question asks, however, about Newton's model of light. And Newton's model of light is known as the corpuscular model. That is, light travels in these discrete particles, which he referred to as corpuscles. Now, if they're going to pass through this slit over here, and we're asked here to draw a labeled sketch of what we want to expect if the corpuscular model was correct. And so we have our light source over here and passing through these slits, and what would we see? Well, we would see two particular bright bands across like so. Now, what obviously is occurring is simply the corpuscles are passing through one slit or the other slit, and so you'd get these two piles, so to speak, of light in terms of on the screen. Now, we need to label it, of course, and then so what we need to label is that the distance between these two lines is basically going to be the same as our slit difference, like so. And you probably also need to identify at least that these are our bright spots or our bright lines over here to represent the fact that they're the result of our corpuscles hitting the screen. Now, we could modify this. The fact is that the corpuscles, as they pass through the slits, might get slightly deviated at the edges. And so instead of two bright lines, we might get a peak that looks something like this, a peak, then nothing, and then another peak here. A little bit of a sort of a spread result over here. But nonetheless, the two peaks must equal the separation in terms of our distance here. Now, in our second part of the question, now we're dealing with the same setup, but now what we get is a series of bright and dark spots, which is consistent of what we actually do get. And in fact, this setup, which is based on Young's double slit experiment, in essence provides evidence for the wave nature of light. We're getting interference on our screen here. We're asked two separate questions. We're asked to work out the angle that is here. Now, and then the second part of the question says, well, let's replace our laser, our 655 nanometer laser, which is a red color, with a green laser, which has a smaller wavelength. And we're asked to explain what would we expect in terms of the changes in the patterns. So let's deal first with the first half of the question, which says, well, let's work out the angle. Now, the mathematical principle at play here is m lambda is equal to d sine theta. That's the formula we use to establish the relationship between the wavelength, the distance between the slits, and the angle that we have represented here. Now, m is equal to the number of bright spots. So, for example, if we want the angle for the first bright spot from the center over to there, then our m is equal to 1. You can see what we end up having is 1, and we have 2 separation. So in other words, our m actually ends up being 2. Now we are given the wavelength. The wavelength is 655 nanometers. So we multiply that by 655 by 10 to the power of -9, which is our nanometers. Now our slit separation is 5 by 10 to the -5. And of course, we're after sine theta, and by association we can work out theta. So in other words, sine theta ends up being equal to our 2 by 655 by 10 to the power of -9 all over 5 by 10 to the power of -5. Now that means our answer for theta, and I'll do the quick calculation, 1.5 degrees. Now, our second part of the question says, explain what happens in terms of the pattern. And again, what we need to do is look at this particular mathematical formula, and I'll rewrite it here again. We've got m lambda is equal to d sine theta. So mathematically, what's going on here? So lambda decreases. Our m obviously can be whatever value we want, but we're interested in what happens to over here. Our slit doesn't change at all, and so our sine theta decreases. So if our lambda decreases, then our sine theta decreases. Now, if our sine theta decreases, then if we look at that angle in terms of our sine theta, if that sine theta decreases, then theta decreases as well. So if theta decreases, the distance between the central bright spot, which is really that central line here, and this is our first bright spot here. Of course, if m is equal to 2, we'll have our second bright spot over here. Then those distances get smaller. And so what we will find is our patterns will get more compressed. So that explains what's going on here. Decreasing the lambda decreases sine theta, which decreases theta, which therefore causes this distance here to decrease, and as a result, the patterns get tighter and closer together. Now here's question 28. Now in this question, we're dealing with two concepts that are found in Module 8. The first is the process of stellar fusion, and in this case, we're referring to what we refer to as the CNO cycle, which is a cycle that occurs in the heavier mass main sequence stars. And again, it's about hydrogen converting into helium, but in this case, rather than the proton-proton chain, it occurs under the CNO cycle. And the second part is the concept of our mass defect, which is in the fourth inquiry question, where we're finding that we release energy if there is a loss in mass in the process. In step X, we have the process of nitrogen breaking down into carbon-13 plus the release of a positron and a neutrino. If you worked out the mass that we started off with and worked out the mass what you end up with and then convert that into energy, and then we express this in electron volts, we get the value of 1.2 mega electron volts. Now in step Y, what we see here is we have the carbon-13 that we had before, and that combines with hydrogen to become into nitrogen-14. And we need to argue, well, the mass defect for step Y is going to be greater, and this converts into energy, than the value that we get here. And that's basically what we do. So our proposed reason is simply to say, well, the mass defect and therefore the energy that gets converted from that mass defect in step Y is going to be greater than the one for step X, but we need to support this with the calculation. So again, quick reminder here that we are interested in the energy as a result of our mass defect multiplied by c squared. So let's start over here, and we need to look at these things here. We need to say, can we work out what the mass defect is? So I have the mass of carbon and our mass of hydrogen. Then if I subtract the mass of what we have left over, which is our nitrogen here, what we end up getting is a change in mass, because this mass here is greater than that mass over here, 13.003. Our hydrogen, or a proton, is 1.007. And then subtract our value of 14.003. Now when we calculate that out, we get 7 by 10 to the power of -3 U, which is our atomic mass unit. Now that is the mass that we have lost in atomic mass units. Now to convert that into the amount of energy we get, then it is simply equal to the mass defect multiplied by c squared. But it's actually quite easy to convert that, because all you need to do is multiply the value of 931.5 mega electron volts, which is the equivalent energy for one atomic mass unit. So all we have to do now is multiply that by our 7 by 10 to the power of -3. So that actually bypasses this. It goes through the same process, but it's a sort of a shorthand way of getting there. And what we end up getting is a value of 6.52 mega electron volts. Now that's clearly significantly larger than the value that was 1.2, so we've argued the case a greater mass defect and supported it with calculations. Let's move on to question 29. Now this question really asks you to understand what's going of motion, in this case dealing with projectile motion, which forms part of Module 5, Advanced Mechanics. But there's no calculations involved here. It's understanding the motion of something undergoing projectile motion in 2 dimensions, but in actual fact there's a 3-dimensional aspect to this. And so what we have is an apple was thrown horizontally from east from a window of a car which was moving with a universal velocity of north. It says explain the horizontal and vertical components of the apple's motion during its flight. Well, let's look at the horizontal components first. And what we have here is our car, which is moving in the northern direction. Now, relative to the car, a person is throwing the apple horizontally out in that direction, which is our easterly direction. Now what that means is that there is a horizontal velocity of the apple already going north when it is being released. We also have a horizontal velocity of the apple going east at the same time. And so relative to the road surface, that apple will be moving at some angle that is a result of both the northern velocity and the eastern velocity. Now remember, this is actually the horizontal motion perpendicular to the direction of the gravitational force or the gravitational acceleration. Now we can't say it's northeast, because that would rely that the apple was thrown with exactly the same velocity east that it is being driven at at north, and we don't know that. And so in that case, it's definitely moving at some sort of angle, but it could be any angle as long as it's between north and east. Now, we need to explain this, of course, so the next step is to say, well, there's no forces, and we're ignoring air resistance here, there's no forces in the direction of motion. It's still traveling parallel to the Earth's surface. And so since there are no forces acting, therefore the motion of the apple is still at a constant velocity at some angle between north and east. So we've explained that aspect. But now let's have a look at the vertical perspective. And so here's our road, and here is our car, like so. A very nice travel. And think that the northern direction is going into that section. So it's going away. What would you see? Now, obviously, that apple will be moving, obviously, some horizontal velocity. But vertically, the apple will be falling downwards. Now, remember, this is just the vertical component. It is still also moving horizontally at some angle. And now, from this perspective, sort of away. But what's happening in this direction? It's accelerating downwards. We're describing the motion, saying that the apple falls from the position level to the window back down to the ground, that we need to explain it. Well, why? Because there is the force due to gravity acting downwards, and this acceleration, therefore, because we assume that the gravitational force is constant, we therefore will have the acceleration being constant vertically. Now, that is, of course, independent of what happens here. So both of those work independently from each other. Constant velocity here, no forces acting. Constant acceleration down, a constant force acting, and therefore we've explained the motion. In question 30, we're dealing with the concept of relativity, which is found in module 7, which is all about light. So it's the consequences of the constancy of the speed of light. Now, in this question, we're having one event. We have a light pulse moving up and down, and that's observed by the person on the train here, but that same pulse is observed by the person on the side of the track here. And you see two paths. That's the path of the light pulse that X experiences, which is that distance and that distance combined. But of course, this person sees that path going there and that path going there. And the result is that what they observe will be different because its motion is relative. Now, we're asked to describe qualitatively how the constancy of the speed of light and the thought this experiment led to the prediction of the concept of time dilation. Our second question asks us to do the calculation, and I'm going to sort of flow from one into the other. Now, mathematically speaking, most situations that we're usually thinking of is that when we observe motion relative to another frame of reference, we say, well, obviously the velocity that we end up getting is simply by the distance we actually measure divided by the time. Now, if this was a ball moving up and down inside the train, most people would say, well, that makes the ball would be measured faster off the train. Why? Well, the fact is that if the distance here is only that distance over here, and that distance is that distance over here for this observer over here, we would say, well, we would observe both of those in the same time frame. And so as a result, we would say, well, bigger distance for the same time frame means a bigger velocity. But for Einstein, he said, well, that's not possible if we're dealing with light. We can have the same formula for C is equal to d over t, where c now is the speed of light. But if we have an increased distance for this observer here compared to this observer here, then this speed can't change. The speed that these observers have to be exactly the same if they're looking at light. And so if the distance gets bigger for one observer, then the only solution is that the time gets bigger as well. And so therefore, the constancy of the speed of light predicts that the time measured for the same event from two different observers in different frames of reference will be different. And that's the essence of time dilation. Now, if I were to then substitute these values for distances over here and use the concept of Pythagoras with these distances over here, I can actually, and in fact that's exactly what Einstein did, you can derive the mathematical formula for time dilation. And it simply says that the time measured for the observer outside the frame of reference of the event is equal to the time naught, which is the time measured of the event inside the frame of reference, divided by the square root of 1 minus v squared over c squared, where v is the velocity of the object going horizontally. You can understand that if this velocity is particularly slow, in other words, even fast for us, but nowhere near the speed of light, this just becomes 1. And so those times end up being practically the same. This only becomes noticeable when we're traveling closer to the speed of light. And that leads us into our next part of the question. It says, well, okay, let's say they measured this time here at 15 nanoseconds in their frame of reference. What's the time that they measure in that frame of reference? Well, we now know, we only think we need now is the velocity, and we're given that velocity is 0.96 times the speed of light. So we just substitute that over here. And so what we get is t naught, which is our 15 nanoseconds. We divide this by the square root of 1 minus, now v squared is 0.96 c squared. Those c squares cancel out, so I can just go here 0.96 and square that. That actually gives me the answer, and it ends up being 53.6 nanoseconds. And that summarizes the answers for the short answer for the HSC. Please remember to like, share, and subscribe. Put a comment down below if this has been helpful for you. And please consider supporting my channel by buying me a coffee. The link is in the description below. My name is Paul from Physics High. Take care and bye for now.